so the next example or rule is a special case of the substitution rule. All right, and it has to do with logarithms. All right, so if you recall the chain rule with the logarithmic function. So if you have a natural log and there's something other than x inside, it could be anything as long as it's something other than x. So remember, the derivative of this is 1 over what's inside times the derivative of what's inside, and then we usually rewrite it as a single fraction. The function inside the natural log is in the denominator, its derivative is in the numerator, all right? And so you'll notice this is a quotient, right? It's a division. And so this is one of those special cases. Remember, we don't have a quotient rule. But whenever we have a division, we can either manipulate it algebraically, or it's going to be a logarithm case. All right, so my next question is, well, what function, if I have a function that's a derivative of the natural log composed with another function? Well, when I have the natural log composed with another function, right, if I've got my ln of some f of x, its derivative is always, right, 1 over what's inside times the derivative of what's inside, right? That's what it's, that's the rule, right? The chain rule with the logarithm. 1 over the function inside times the derivative of the function inside, which can always be rewritten as this type of fraction, right? So remember, we're working backwards, antiderivatives. So if I have a fraction, or if I can manipulate a function to get a fraction where it's a derivative of a function divided by that function, that type of quotient, that type of division, then my original function should be a logarithm, right? My antiderivative of a this would be the antiderivative rule for logarithms. And so we get the following theorem. It's actually a theorem that can be proved. If I get this ratio, I want to find the antiderivative of it. So if I have in the denominator a function where its derivative is in the numerator, and sometimes we do have to manipulate it to get what we want, right? We have to use a little algebra if I need to do any, a little algebra manipulation to get this. If that's the case, then the antiderivative of that is the natural log. Now remember, the original function could have existed for negative values, right? The original function could exist for negative values. And so whenever we do an antiderivative of a logarithm, the logarithms don't exist for negatives, and so we always have to do the absolute value in order for the entire function's antiderivative to exist, so we could find the entire area under the curve if I want to, using the fundamental theorem of calculus. So you always have to remember that absolute value. All right, so it is a substitution rule. If I take this fraction, so this is sort of kind of the simple proof of it. If I take this fractions and split it into 1 over f of x times the derivative of f of x dx, well, this is just the substitution rule, right? If I let u equal f of x, then du equals the derivative of f of x dx. So we replace this with u, we replace this with du, right? 1 over u dx, which 1 over u is the natural log of u, absolute value. You can't forget the absolute value plus a constant. And then you replace back to get my general antiderivative is the natural log of the absolute value of whatever the denominator function was. Right? And so there's really not a whole lot of work you have to check. You basically just have to check that this is true. You have that. Alright, so let's do the first example. So I've got 2e to the 2x divided by e to the 2x minus 10. Remember, I don't have a quotient rule. It doesn't exist. So the only way to find an antiderivative is to either manipulate it, get rid of the division, or it's a logarithm case. And so this is a logarithm, but you do have to check. The denominator is f of x. So again, that would be the u part, which would be e to the 2x minus 10. The derivative of that, well, e to the 2x would be e to the 2x times 2. The negative 10 will zero out. If I rewrite that, well, that is the numerator, right? And so I do get the expression, the denominator's derivative is in the numerator, right? And as soon as I recognize that, I know the answer. Well then, if that's the case, the only possibility for my general antiderivative is to be the natural log of the absolute value of the denominator function, the bottom function, which is e to the 2x minus 10. And then don't forget, that's the family of them, so there has to be a constant tacked on there at the end. Alright, so I'm going to stop there. I'm going to do the next examples of this special case in the next video.